Good evening, everyone. We very warmly welcome to today's webinar on leverage AI/ML for next generation of wireless communications in physical and higher layer perspective. I am Ravindu Hera, your moderator for today. On behalf of IIT Young Professionals Sri Lanka, I extend my sincere thanks for all for joining today. The session brings together researchers, the professionals and the students, and the passionate about AI and next generation wireless communication technologies. We are excited to explore how artificial intelligence and machine learning are transforming communication system in both physical and higher layer. It's my pleasure to introduce today's distinguished speaker, Dr. Sapcha Bhattacharya. Dr. Sapcha is an assistant professor in Barkwell Engineering College, and he currently deputed at the Residential Girls Polytechnic, Golgat, both under the government of Assam and the India. He earned his Bachelor of Technology in Electronics and Communication Engineering with the University Court from Assam Don Bosco University in 2013. He obtained his Master in Signal Processing and Communication with first class from the Guwahati University in 2016. And he completed his PhD in Wireless Communication from IIT Guwahati in 2023. Currently, Dr. Sapchashi is engaged in postdoctoral research in physical layer and cybersecurity for satellite and space network. He collaborating with professor from the University of South Florida in USA. We are truly honored to have him today. Without further delay, I invited Dr. Sapchashi to begin his presentations.
Thank you. Thank you so much, Ravidu, for the very warm introduction. I'm grateful for the invitation to IIT Sri Lanka Network and mostly to you and also your honorary secretary for the very, very kind invitation. So good evening all. Good evening all participants. It is a very warm and pleasurable moment for me to be able to share some of my insights regarding AI/ML and its evolution of the next generation wireless communications in this next 1 hour with you. Although given the paucity of time, it will be an overview of the domain. However, I will try to go into some technical details of the work as well. Because in 1 hour, we cannot really cover the entire essence. So I'll go into the details as much the time will permit. Now, without any further ado, I'll share the screen. And I'll just ask Mr. Ravidu to kindly check if you are able to see the screen. Yeah, you can see my presentation, I hope.
Yeah, Doctor. Now you can see.
Yeah. Okay. So I will have a couple of multimedia videos. So we'll have the check on the audio directly during the time when I show you the video. So with this, I'll start off directly with my presentation. So good evening to one and all present here. So I am grateful to the IIT Young Professionals Network Sri Lanka for providing this opportunity to share some of my insights on leveraging AI/ML for next generation wireless communications. I'll be discussing slightly on the aspects of the physical layer aspects as well as I'll touch upon some of the aspects related to the higher layer communications, because communications is a highly interdisciplinary domain and it involves all the different layers of communications available on the OSI interconnect model. Myself, already I'm introduced. Myself, I am Dr. Sabyasachi Bhattacharya. I'm an assistant professor in the Department of Electronics and Telecommunication Engineering, Barak Valley Engineering College, Karimganj, and presently I am attached to the Residential Girls Polytechnic, Golaghat. Both of the institutions are constituent units of the government of Assam in India. We are fully state-funded government institutions. A brief content about what I am going to cover over the next 1 hour is firstly, considering the fact that we will have some students here, either bachelor's or master students. I'll start off with a very basic evolution of the modern day communications right from the journey from 1G to 6G with the AI powered evolution. And slowly I'll move into the depth of the AI/ML technology. I'll go into some of the stochastic models and how those stochastic models have subsequently been modernized using the AI and ML technologies. Also, I shall be showing you some of the aspects or some of my works with my team regarding the stochastic modeling, which is AI and ML based in the present. And we will also see some parameter optimization aspects towards the end of the talk. I am properly audible, right, Ravidu? Am I audible clearly?
Yes, doctor.
Okay, thank you. So, if we speak about the journey for from the first generation to the next gen 6G, if we look at it at a glance, then we'd see that basically what has happened is right from the 1980s, very sharp evolution has taken place over the communication generations and the communication technologies and the associated devices. Right from 1980s, where we started off with the simple voice calling. In 90s, we were starting off with the first digitized text messaging, whereas in the 2000s, we came up with the internet access, and that internet access aspect actually got more modernized with the internet access of the modern days, that is the 4G communications, which was replaced very fast in 2020s by the smart society which we are presently in, and that is basically structured as the 5G communications now. And now already we have a communication environment around us, or a wireless communication scenario where the devices are already smart and they are able to self configure themselves. But we are now looking at not only a smart society, but rather by 2030, that is the 6G deployment target as per the ITUT standards. So that we are looking at a intelligent society basically. And when I say intelligent society, I means devices which can self interact with each other, devices which can not only interact between them, but they can also interact with the human being in reality or with a virtual fragmentation. So if I consider the technology has also evolved very rapidly. Right from the 1G voice call where we would connect to AMPS or the NMT, in 2G we are connecting to the GSM, basically the the globular structure for the satellite, the globular structure basically for the mobile communication, the global system for mobile communications rather. Whereas with the internet access coming into the picture, we also started exploring digital codes for our communication, wherein came up the WCDMA system. This got a very fast evolvement with 3G getting replaced by the 4G systems, where we came across the LTE, that is the long-term evolution, where we came across beam-based systems, beam-forming-based systems, uh, and the basic framework or the basic foundation stone for intelligent systems started off from the 4G systems, in fact. Whereas in 5G, the antenna technology evolved very massively with us getting connected into MIMO, that is the multiple input and the multiple output antenna systems. And the frequency of the waves also played a very crucial role, wherein we were having the millimeter wave technology, that is frequencies which were as low as in the range of millimeter. The wavelengths were as low as in the range of millimeters, whereas the frequency went up to high ranges of the gigahertz. And in 6G, we are trying to expand that frame even higher, and that is why I have intentionally kept this bracket blank, because the spectrum and the technology for 6G is not yet completely decided. We are still working on it, and thereby it shows the under construction aspect mentioned here. So we are still looking at what would be the possible technology which would be focused upon in the 6G communications. So the same leap over, if we observe on the diagram to the right, which is from Forbes, basically, it is that from 1990s, where we were observing voice calls and SMS over 2G, in 2000s, we came across the high-speed browsing, that is in 3G communications. Whereas in 4G, we would have the video conferencing and mobile TV coming into the picture, wherein the first time we were introduced to the online OTT platforms, 2010, although it did not become very popular. But with 5G in 2020s, that is the advent of where the COVID scenario also came in, we were using the mobile internet, and we were using the mobile OTT platforms as well as the different online platforms at a vast rate, and also the AR/VR, that is the augmented reality and the virtual reality, through which we could observe or we could design our necessary systems, or our necessary things could be got ready by evolving them over a distance using the AR/VR technology. All these things came up amalgamatively, and not to forget, IoT also came up very rapidly with the 5G technology, hand in hand with the 5G technology. So this is the thing. Now we are evolving now slowly towards 6G, where we are targeting an intelligent society basically with us. So let us see this is a glimpse of the evolution of the communication. Let us see for the interest of the beginners. I have just amalgamated one video here where you would see how exactly your mobile networks have evolved from 1G to 6G. I hope you will like the video. I'd request Ravidu to, I'll just start the video. Please give me a feedback on the audio, whether you are able to listen. Also, all the participants, if you could just give me a feedback on the chat box, if you are able to listen or not.
Mobile networks from 1G to 6G. Welcome back, tech enthusiasts. Today, we're diving into the fascinating world of mobile networks. From those fuzzy first calls.
Are you able to listen to the audio? Can you give me a feedback?
Yes, doctor, we can hear.
Okay. I'll just start the video from the beginning. Yeah.
Right.
So I hope you will like that video. I'm restarting.
Mobile networks from 1G to 6G. Welcome back, tech enthusiasts. Today, we're diving into the fascinating world of mobile networks. From those fuzzy first calls to crystal clear video chats, blazing fast downloads, and the seamless connectivity we often take for granted, we're breaking it all down. From the humble beginnings of 1G to the futuristic promises of 6G, let's explore how each generation has revolutionized the way we connect. We're talking about the technology that's become so ingrained in our lives we almost don't even think about it until we lose signal, am I right? 1G, the dawn of mobile phones. Let's rewind back to 1983. This was also the year the world said hello to the first generation of mobile networks, 1G. It was like stepping out of the Stone Age and into the digital age. Okay, maybe not that dramatic, but it was huge. For the first time ever, we could make calls without those clunky landlines. Imagine, no more tangled cords or being tethered to one spot. But hold on, 1G wasn't all sunshine and roses. Remember those gigantic brick-like phones? Yeah, those were the OG mobile devices, and they were notorious for their spotty coverage, dropped calls, and let's be honest, the audio quality, let's just say it left a lot to be desired. But hey, it was a start. 1G paved the way for the future of mobile communication, and for that, it deserves a place in the Tech Hall of Fame. 2G, the texting era, begins. Fast forward to the 1990s and the rise of the internet. This is where 2G enters the scene, bringing with it the power of digital communication. Remember those old Nokia phones with the indestructible bodies and Snake pre-installed? That's 2G. This new generation of mobile networks ushered in clearer calls, better security, and most importantly, it gave birth to the short message service, better known as SMS or texting. Remember those tiny keypads and the struggle of typing out a message with T9? It was all worth it because we could finally send messages instantly. 2G also laid the groundwork for mobile internet, but it was slow, clunky, and honestly not that great. But hey, it was a stepping stone to something even bigger and better.
So at this phase, I'd just like to pause the video and I'd just like to mention you that this is a very common sight wherein you are observing this single monopole antenna, which is a very common sight when the mobile phones were initially introduced and we could get rid of the clunky landlines. But still the structure of the mobile phone was very, very much old generation, or rather I should say the structure of the mobile phones was very generic. But now, after this, in the later part of the video, you will see that suddenly with the arising of the 3G generation or 2.5G generation of the mobile telephony, everything, all the features regarding a mobile telephony changed actually. And that is where the communication took a big leap actually. So I'll just restart it.
Next up, 3G. Welcome to the mobile internet. The early 2000s saw the rise of 3G, and let me tell you, this was a game changer. Remember the flip phones and the early smartphones? They were powered by 3G, and suddenly the world became a whole lot more connected. We're talking faster data speeds, which meant we could actually browse the internet on our phones without wanting to throw them at a wall. Websites loaded faster, we could download music, legally of course, and video calls started to become a thing. 3G truly transformed the way we interacted with the world. It was the catalyst for the mobile revolution, and it set the stage for the smartphone era we live in today. 4G, the LTE revolution, 4G, or as it's often called LTE, took mobile to a whole new level. We're talking lightning fast download and upload speeds, almost as fast as home broadband connections. Streaming services like Netflix and Spotify became the norm, and suddenly we were watching HD videos on the go without a second thought. Mobile gaming exploded with 4G. Remember when you had to be connected to Wi-Fi to play a game without lag?
The features that we were using
Those
with the
days.
mobile phone. Suddenly from that short text messaging, it got up to playing fancy video games and playing up the digital or utilizing the OTT platforms at a massive rate. So this is how quickly it changed in between the third generation and the fourth generation.
Were long gone. We could download and play graphically demanding games anywhere, anytime. 4G enabled a seamless mobile experience, and let's be real, it's hard to imagine our lives without it. But as always, the tech world never sleeps, and there's always something new on the horizon. 5G, the quantum leap. Enter 5G, the next generation of mobile networks. This isn't just an upgrade, it's a complete paradigm shift. We're talking insanely fast speeds, like downloading a full HD movie in seconds. But it's not just about speed. 5G also brings incredibly low latency, which is the time it takes for data to travel from your device to the network and back. This means real-time gaming, virtual reality, and augmented reality experiences are going to be mind-blowing. 5G will also be the backbone of the Internet of Things, with billions of devices connected seamlessly.
So essentially, everything connected to everything, or the Internet of everything, is basically the future of 6G and the later 5G, that is the beyond 5G.
Making our cities smarter and our lives more efficient. Imagine self-driving cars communicating with each other, smart homes that adjust to our needs, and even remote surgery becoming commonplace. 5G is still in its early stages, but the potential is limitless. 6G, the future of connectivity. We've come a long way from those clunky 1G phones, haven't we? But the future of mobile is even more exciting. While 5G is just getting started, researchers are already working on 6G, and it's going to be revolutionary. Imagine speeds 100 times faster than 5G, allowing for near instantaneous data transfer. We're talking about a world where the lines between physical...
This part of the video shows the virtual reality, or basically how you can have the AR VR sort of an interaction with your like where we are talking about a digital twin where a human being can virtually interact by being at the same place where his or her friend is. So that is how the future of 6G looks like.
Digital realities blur. Think holographic communication, immersive virtual environments, and even the ability to control devices with our minds. Okay, maybe that's a bit further out. 6G will be powered by artificial intelligence, creating networks that can learn, adapt, and optimize themselves in real time. It's going to be fascinating to see how 6G unfolds and what new possibilities it unlocks. And there you have it, the incredible journey from 1G to 6G. From those crackling voice calls to the mind-blowing possibilities of the future, mobile networks have come a long way. Which generation had the most impact on your life? Let us know in the comments below. Was it the freedom?
Okay, so at this point, I will stop the video. I hope all of you liked the video. If it will be very good if you can give me a feedback on the chat box. I hope the video was informative for you as I progress. I hope if somebody could give me a feedback on the chat box. That would also help me to know if you are with me on the same page. Okay, so I have some. So thank you. Okay, so now pushing the boundaries beyond the 5G wireless communications. So essentially, whenever we are talking about the 6G communications, we should realize or we should appreciate one thing, that 6G is not really a newness of the technology as compared to the 5G. It is basically about pushing the boundaries or extending the limits that 5G has set forth. 5G already speaks to you about certain aspects of very, very ultra reliable communications like the URLLC, where we are talking about ultra reliable communication as well as low latency communications, where the round trip delays would be less than 1 millisecond sort of a thing. And also we are talking about the UMTC, we are talking about EMBB. So these are some of the related technologies where we are talking about extremely reliable communications, where we are talking at insanely low BER or symbol error rates in the ranges of 10 to the power minus 8, 10 to the power minus 9. We are talking about extreme massive connectivity and sensing, where a signal strength, even in the micro watt level, could be very, very easily sensed. We are talking about very low power devices where the processing powers would go very low. At the same time, we are talking about very, very high end speed capacity and high capacity communication, where not only the peak data, not only the total capacity of the network would increase immensely, but also the peak data rate would be very, very high. So this is how entire 5G picture looks like. But essentially, the purpose of 6G communication is also same. Just that what is the difference between 5G and 6G is that if we are having URLLC communication in 5G, that is, we are having the 1 millisecond sort of a round trip latency in 5G, we need to sustain it over a longer period of time. And that is basically the goal of 6G. That is basically making 5G solutions more realistic, or 5G solutions more acceptable in practical situations. Why that has been a problem with 5G? Because if you would understand, as I had told at the beginning of the lecture, that that is basically we are using the millimeter wave spectrum. So now the millimeter wave spectrum is a low frequency, it is a high frequency, low wavelength spectrum. Now, if it is a high frequency and low wavelength spectrum, the waves are of short wave. That is the short wave in nature. Now, if it is short wave in nature, the signals will not be that reliable. That is, the signal will be there for a particular instant of time. At the next instant of time, the signal will be suddenly gone. So that problem 5G is facing. Even if when you are using your 5G mobile packs, I'm sure in Sri Lanka also, the 5G mobile packs would be active by now. So when you are using those 5G mobile packs, what is happening is basically suddenly the call drop is happening. That is a very unreliable patch of communication or time patch of communication is observed. Now, although when the connectivity is full, then we are moving that unreliability. And that is what is the primary goal of the 6G communications. And obviously, as all these features are mentioned against the 6G, so definitely just like 5G, all the features of 6G, all the features will also be included in 6G, but with a broader horizon. And that horizon basically means that we are extending the reliability levels of our system. So it massively works upon the increase of the reliability levels of our system. So now if I shift from the basic discussion to slightly advanced discussion, that is, we are talking here the transition from the 5G generation to the beyond 5G and 6G communications, which are very close to each other. So what would be the key enabling technologies for the 6G networks? The key enabling technologies for 6G networks will be all of these. Actually, all this big sphere of horizon would come into the picture here. So obviously, one of the key aspects when it comes to the processing, or when it comes to the development of the different algorithms related to communication, it may be any sort of development in terms of channel estimation, in terms of your traffic routing, in terms of floor placing. It can be any sort of a domain of communication, but the algorithms will be AI/ML dependent algorithms. And exactly opposite, on the diagonal side, I am talking about the quantum communication. So now I would try to relate what you mean by AI/ML and quantum communication. So AI/ML would give us the necessary software algorithms, which would be very efficient and could reprogram themselves very efficiently to give us the necessary estimation or give us the necessary level of communication performance that we need from our system. But it would only give us the communication aspects, or it would only give us the software related aspect. What about the hardware domain? That is, how or on what actually will you implement that very critical or very ultra critical sort of a algorithm that you have developed using this AI and ML? You will need a hardware where you are not deciding a decision level between 0 and 1. We are deciding the decision level as something which is a combination of 0 and 1. That is a superposition of 0 and 1. And that hardware, where we are not talking about 0 and 1 fixed levels, but rather we are talking about fuzzy level states. Those are quantum communications. Basically, those levels of communication, those are known as the quantum levels or the quantum hardware. So this is AIML, and on the other end, we have the quantum communication. We would have different other technologies also, but AIML and quantum communication would be the two primary technologies based on which the paradigm shift will be achieved as compared to 5G and moving up towards the next generation 6G. And along with that, the different types of techniques which were there in 5G, like beamforming, the performance of beamforming and beam alignment would change or would improve. That is one. Ultra massive MIMO. So we are having massive MIMO where we were considering base stations of the range of around 256 antennas at the base station. Now we are talking about 512, 1024 number of antennas at the base station. So which is basically the concept of the ultra massive MIMO. We are talking about millimeter waves where the entire 6G spectrum can either be a millimeter wave based spectrum or it can also be a terahertz based spectrum. So I have mentioned here terahertz communication, which is in the terahertz frequency range. So these are also shortwave communications, just like millimeter wave, and have their different type of physical and spatial characteristics. And satellite communications would be redefined as soon as we are coming to the 6G state, because we are talking about shortwave, and we are talking here about UAV, or we are talking about LEO satellites, which are very close to the Earth orbit. And satellite communications thereby would now not only be a part of your entire, a part of only very mission critical sort of activities, but rather it would also be a part of day-to-day activities such as food delivery, such as app delivery, as it has already become popular with the different mobile apps that we are using. So we are already having a number of apps, and most of them are GPS or satellite controlled. AI-enabled 6G network will have these different types of operations. So you can see here, the operations are put together. Both we are having the physical layer type of operation as well as the higher layer type of operations. Suppose if you see the channel estimation, so all of us know that the physical wireless channel is a unknown commodity, or it is an uncertain commodity, and no one knows in reality, or no one knows in its true sense what is the nature of the channel. We can only estimate the channel, and we can cancel the effect of that channel on our received signal. So that for that, channel estimation is one of the most critical parts of our communication system. So the channel estimation procedures with 6G and AIML based approach coming in, the channel estimation procedure will change. Similarly, the modulation recognition. Modulation recognition means if in the 6G environment, we can have almost signals coming into your receiver which are having any sort of modulation schemes, such as the any version of PSK, any version of QAM, any version of combination of the PSK along with Alamouti scheme, and so forth. So it can be almost any modulation. So it becomes very, very highly critical for us to analyze what type of modulation scheme is followed, or what type of modulation scheme is there in the signal that you are receiving. And for recognizing that, we have the AIML architecture in place. So these two are mostly physical layer communication aspects. This I will be discussing with some research work that has taken place in the recent things. Also, we have a number of aspects which are a combination of physical layer and higher layer aspects, like energy optimization, how you would optimize the power. We have network layer aspects like mobility management, how to assess and how to control the fault that is there. Also, we have physical layer aspects like radio resource management, where you are how you have to assign the different radio frequencies to the different users, because high number of users will have access to the same radio resource. So name any application in wireless communications, and it will be in 6th generation networks, it will have the AIML impacting it. So that is what is shown in this particular figure. And if you talk about the key technologies, as I have mentioned, AIML and quantum communication will play a big role. Today's lecture that I have planned for you is mostly focusing upon the AIML based wireless communication. I have intentionally kept the quantum aspect out of the picture because both the things cannot be covered effectively together. Definitely, if given the opportunity, I can deliver another aspect on the quantum communication as well separately. Okay, so now after this quite a period of the lecture, I also have another video where this particular we are talking about Qualcomm and Nokia Bell Labs merger, where they are trying to implement AIML based technologies into the next generation wireless system. So this video will give you whereas the previous video was a very elementary sort of a video, this video would give you some technical specifications or some insights into how realistically Nokia and Bell Labs have merged together or collaborated together to realize the next generation wireless communication. So I hope you will like the video. I am starting the video.
Qualcomm Technologies and Nokia Bell Labs are working together to unlock the full potential of wireless
Please
AI.
give me a feedback on whether you are able to get the audio or not.
Creating a
Give it on the
wireless
chat.
system that learns and improves
can
over
use it.
time across different devices, networks, and technologies. By combining the power of AI with wireless systems, we're opening the door to a new era of smarter connectivity. To understand how AI can improve our experience, let's examine how it impacts one of the most essential tools in optimizing wireless systems, channel state feedback. Channel state feedback helps the network figure out the best way to send data to your device. As wireless conditions change, so does the optimal direction a transmission takes from the network to the device. Channel state feedback, however, allows the network to find those ideal avenues by generating precise beams. Using AI, we can dramatically improve how the system tracks channel state feedback, making the network and devices smarter and more efficient. Implementing AI effectively into wireless communications, however, is a complex matter. In even the simplest wireless system, there's a network and a device, and both utilize their own AI models. Those models need to cooperate. That's the heart of Qualcomm and Nokia's joint research.
So this is how there is a interconnect and a communication where the entire process or entire communication encoder and the decoder, that is the communicating transmitter and the receiver, now essentially becomes a AI encoder at the transmitter and a AI encoder at the receiver. And both the encoder and the receiver have to synchronously cooperate with each other so as to have the necessary effective communication. So we are making the process simple because the normal communication is all statistical. Now we are removing the statistics behind it and we are putting the learning based systems inside it. Although statistical rules are there, but still predominantly it is learning based. So the encoders and the decoders are easier to design, but they have to work synchronously. That is the challenge in this type of communication.
Getting AI in the network and devices to work together to amplify their benefits. To test their AI-powered solution, Qualcomm and Nokia Bell Labs set up a 5G test network using cutting-edge equipment and mobile devices powered by Qualcomm 5G modem RF.
So we begin with AI models, which are trained with a shared data set. We use a technique called sequential learning, where the model in the network device is trained first, and then the model in the mobile device is trained. We use a shared data set to make sure that they speak the same language as they learn, without requiring different companies to share detailed information about their implementation. After the AI models are trained, we put them into action. The network device sends pilot signals down to the mobile device. The mobile device feeds that information into its AI model to get a feedback signal, which is sent back up to the network device. The network device uses its AI model to decode that feedback and then use it to determine optimal beam patterns to focus the signal energy right to that particular mobile user.
We've been very pleased with the results so far. In our tests, we found sequential training has substantially improved downlink throughput compared to traditional approaches. This shows just how much AI can enhance the performance of wireless networks. Since the collaboration between Qualcomm and Bell Lab, we have
this car movement that you are observing here, this is basically for the outdoor communication. You were observing earlier that a person was pulling a cart and moving his transceiver. So that was for the indoor mobile communication. This car movement is basically for the learning and for getting a grasp of the entire environment, the wireless environment in the outdoor mobile communication scenario.
Expanded our scope in terms of research and testing. We have bring our models in more tested areas compared to last year. So this year, our primary goals will be ensuring not just the interoperability, but also the scalability of the AI models. We want to make sure it can work in different environments. We compare the performance of model, which is trained with data from various locations, against the performance of hyperlocal models trained with specific cell site data. In every case, the AI system performed consistently.
When we tested the models in situations where they hadn't been specifically trained for, we found that the system still worked well.
As this person is mentioning here, it is very important to note that AI models, if they are adopted for the wireless communication, and as it is a very highly uncertain environment, the physical layer wireless channel or even the higher layer wireless channel. So even if a particular AI model is not trained for exactly a particular situation, if it has been trained for a nearby situation also, it can adapt and perform very well. So that is a very key thing to note, that you don't have to train your system very, very extensively also.
So this means that AI models don't need to be trained for every specific site, which makes it much easier to deploy and use. For example, it would work just as well in a busy urban center as it would in a quiet suburban neighborhood. In the end, the AI-driven approach we used proved to be simple, powerful, and highly scalable.
As we continue our journey toward building smarter, AI-native wireless systems, these innovations will pave the way for the next generation of wireless technology. Stay tuned for more as we continue to push the boundaries of what's possible.
Yeah, so this is Qualcomm and Bell Labs, Nokia Bell Labs collaboration. It is a very active work that is going on in the domain of 6G. And I would urge here that I believe researchers or students who have joined here are interested towards wireless communications. So I would urge the students to follow their updates and also try to become a part of this very big collaboration, as it will highly boost your careers. I'll proceed further. Okay, so now what are the some terminologies that you need to know about AI and ML in context with the next generation wireless communication? Because AI ML essentially is not a new aspect. The incorporation of AI ML into the wireless communications is a new aspect. So what are the some basic terminologies that you will have to use in the wireless communications to understand the AI ML aspects better? So if you see that black line that I am dividing this entire screen upon, it means that the above part is basically the training model or the training part of your AI/ML model, and the lower part is the real-time communication or the real-time implementation. So the first thing that you need to know is the data set upon which you are doing the training. So that data set will always be pre-labeled, because in wireless communications, we are essentially talking about the supervised learning, where the output levels as well as the output levels are known to us. That is, we know what are the inputs and what will be the outputs from the system. So these are known as pre-labeled synthesized data. Now, as all of us know, the time series data cannot be processed directly. We need to have some amount of transformation. It may be a DCT, it may be some filtering sort of a aspect, it may be some DFTs or frequency domain transformation. So we will have some transform over this pre-labeled synthesized data, and it will move into the train network. Basically, it will be moving into the training network, basically, where that training network will move forward and we will have a trained model. And this structure is basically the AI/ML model, which in today's generation, at today's level, we are talking about the DNNs, that is the deep neural networks. We started off with the basic layer level artificial neural networks, and today it has reached to a stage where we are having multiple number of hidden layers or high number of hidden layers, and this is basically the deep neural network. So now this is the trained model, and this same trained model will be placed here as a pre-trained model, where we are basically dealing with the actual communication. So what I mean to say is the entire transmitter or the entire receiver now basically is replicated by this one single DNN model. And what we do in real time, we are passing off the new signal, which is similar to the labeled signal. We are transforming it just like we did in the training phase, and we are fitting it to the pre-trained model. From the pre-trained model, it is giving us the necessary classification. Classification here means that if you need to classify what is the modulation scheme, it will give you the correct modulation scheme out of number of modulation schemes. If you need to classify what is the correct estimate of the channel, it will give you the correct estimate of the channel among number of wrong channel estimate. So that is the power of the AIML model. So these are some of the terminologies that you actually need to know regarding your next generation wireless communication in line with AIML. AIML areas, the target areas of AIML in next gen wireless. As I have mentioned you, AIML is applied in wireless communications at different layers of communication, starting off with the physical layer communication, where we will be discussing on channel estimation, modulation identification, also a little bit on beamforming. It can also be deployed to the semi-physical, semi-data link layer, that is the MAC layer, which forms the interconnect between the physical and the network layer. It can be used for higher layer applications, purely higher layer applications like the network layer for mobility management, routing of the correct path of the traffic, also for clustering operations. It can be used. Also for transport layer and very, very high-end applications, application aspects, that is the front end. That is basically the application layer. In this talk, we will be keeping our discussion limited to physical layer, little bit of MAC and network layer. So now let us start off or move to one of the works actually, some of the works that have been done in the near future. So in the near past actually. So one of the works by Silva, who is actually from Sri Lankan origin, he performed one very important work actually in the Journal of Wireless Communications and Networks in 2022. It was published. So this is an AIML based channel estimation where he has very categorically classified what could be the different types of channel estimation aspects. So as per his classification, the channel estimation aspects could be training process based channel estimation. It could be training process based, where the training could be either data driven or it could be model driven. That is, you are training the system based on the data, or you are training the system specific to the model, that is the DNN or the recursive network or the concurrent networks. It could be the supervision learning level. That is, it could be either a supervised type of a model or an unsupervised type, or within a supervised, it can also be a reinforcement type of a model. It could be depending upon the strategy also, whether you are doing the training online in purely online mode, that is when the actual communication is happening, you are training your system, that is known as online. Offline essentially means that you are training the system, you are training this system as an offline mode. Offline mode basically means priorly you are training it and then you are starting the training basically. And the system implementation could again be of different types. It could be either a AI-aided model based, it could be either a AI-aided block type based, or it could be either a joining function based. So AI-aided model based basically means you are implementing the entire system depending upon what kind of model you are handling. That depending upon that, you are categorizing your channel estimation. Block type means you are analyzing or you are designing the system based on what is the data at hand, what type of data you are having or what type of training data you are. And joining function based means you are taking care of both the model, that is whether it is the DNN, whether it is the CNN, and you are also looking at what type of data set you are having at hand. If you are having both the aspects, then it is joining function based estimation. So these are the different types of channel estimation that can be there as per Silva's work that is published in 2020. Another similar work here by Luo can be observed. This is an AIML based channel estimation process. So what would be actually inside the transmitter and the receiver of a AIML based wireless communication system? That would be a big question. So if you see very carefully in the transmitter as well as the receiver, in the online deployment stage, that is where the practical communication is taking place, you can see all these are the generic blocks. If you see the transmit symbols, the serial to parallel conversion, IDFT, insert the CP, that is the cyclic prefix, parallel to serial conversion, passing off through the channel. Then again, serial to parallel conversion in the receiver, remove CP, DFT. All these are basically the same blocks that are essentially there, the same blocks that are there as in case of a routine communication or a conventional non-AIML based communication. But what is the difference? The difference is this offline training phase, where since in this you are estimating the channel, so I am using the transmit symbol and I am also giving a feedback to the system about the channel models. So now with these two data combined, we are having the simulation data. Basically, we are considering the simulation data aspect basically. And that simulation data we are using basically to combine the DNN model. This is basically the deep neural network based model. This is a DNN model. Now that DNN model, now we are pushing it through to the recovery stage of the data. So in a receiver, the practical receiver is not a conventional statistical receiver, but it is a DNN based receiver. So if I say, or if you ask me what is the difference in the transmitter and the receiver for a communication system or a wireless communication system, I would say in primarily in the receiver, the recovery data stage or the channel or the estimation stage or the receiver or the recovery stage, that stage is replaced by a DNN system. That stage is basically replaced by a DNN based system or a learning based system. That's all. That is the change that has happened when we are doing channel estimation instead of statistical approaches, when we are using the AI/ML or the deep learning based approach. So this is for the channel estimation. If you are trying to estimate the channel, this was a work published in Electronics Letters 2023. If you are trying to detect the modulation, what type of modulation system is there, the process would be same, exactly the same. Here, since it was for channel estimation, with the symbols, I am giving the information about the channel model. In the next work, it is about modulation scheme. So with the symbols, I am giving the information about the modulation type. What type of different modulations can be there possible in the system. And with this data combination, the data transfer, my neural network or my DNN is getting trained. And once it is trained in the online testing phase, you can see there is all the other blocks are the same. You can have a note on the yellow colored blocks. Both these blocks, the detection network and the modulation recognition network, will work in synchronization with each other. They will be basically working off with the synchronization of each other. So this modulation recognition network will basically do what? The modulation recognition network will basically recognize what type of modulation has actually come down in the received vector. It will try to detect that. And once it is able to detect that it is a FSK type of modulation scheme or a PSK, say 4 PSK or 8 PSK type of modulation scheme, then it will trigger the detection network. There should be an arrow here, but I have not given because I have given the same color. That modulation network, recognition network will trigger the detection network, and accordingly the detection network is a multi-varied system which has all the receivers designed inside it. So once it recognizes that this is a PSK system or a PSK based signal that is coming in, or 2 PSK or 5 PSK or 4 PSK or 8 PSK, then the detection network will automatically tune to the equivalent receiver. That is, it will go into a 8 PSK mode or a 16 PSK receiver mode, and accordingly it will give us the detected signal back. So it is as simple how to detect the modulation. So even for modulation detection, ultimately only the receiver system is changing, or at the receiver we are using this DNN structure basically. That is how simple the incorporation of AI/ML is into the wireless communication settings. It is just changing a few blocks and not the entire structure of the communication basically, or the communication chain. AI/ML is also supporting beam forming at the physical layer level. That is alignment of the beam so that the power is maximum or the power is optimum at each time to the receiving device. Also at the higher layer, it is supporting the beam management, which I am coming to in a moment. Beam forming, when I say, there could be two types of beam formings in a MIMO system. If it is of full dimension, it could be the elevated beam forming, where our antennas situated at the top are only focusing on the users at the top, that is the higher stories of the building. And azimutha beamforming would be when we are focusing on people at the ground surface level basically. And we need to have simultaneous elevated and azimutha beamforming in real time so as to have the waves. Now this downlink beamforming, actually what it does is basically it focuses on the signals from the base station into a narrow beam. So we need to narrow down our beam, or we need to optimize our beam in the best possible manner so that we can say that basically we are narrowing down the beam aspect as much as possible so that the coverage or the signal accuracy increases. Now, if that is happening, then what happens is basically this azimutha beamforming, these beam lobes that you are observing, these here in the picture are quite thick, but when we are using AIML based approach, these beam sizes or the widths will be varying, or it will be constantly be thickened and thin. That is, it will constantly tune so that the narrowmost beam can reach the end user. So that is how it helps in beam forming. How does it help in beam management, which is a higher layer aspect again? So you can observe this structure where you can see this red small car, which is getting signal from this particular base station at this point. And you can see this truck, which is getting the signal from the base station that you can observe at the back. All of us realize that at some point of time, this red colored car and the truck will cross each other's position. And as soon as it crosses each other's position, although now the red car is getting the beam from this particular green colored beam, and the truck is getting it from the blue colored beam, as soon as it changes the position, there should be an instantaneous switch, or the beam should be managed such that the car now gets it from the blue colored beam and this truck now gets it from the green colored beam. How does it, how can it happen? This entire video in the form of some images with the camera, it is constantly being tracked, and the features of this image, mind it, not the image, but the features of this image are fed to this very highly complicated DNN structure where there are a number of hidden and activation layers activated. So the features of this image are constantly fed into it so that it has a momentary track of when exactly this truck is crossing the car. And once the truck is crossing the car, instantly the beam will switch so that the green beam connects to the truck and the blue beam connects to the red colored car. And this is a classic example of the beam management process, as has been illustrated by Manjares in his work, that is 2023, Sensors 2023, in the 6G context basically. And that has to happen in a very instantaneous manner. It cannot be, there cannot be delays while in this changeover, otherwise the signal will be lost. And we in 6G standards, we cannot afford, we have to do the transferring or the handoff in moments. It has to be instantaneous, and it cannot have delays or lags basically. So these are the aspects of beam forming and beam management in connection with AI. AIML has also changed cyber security at the physical layer level. We are already aware that in the regular cyber security aspects, the higher layer level computations, cyber security is affected deeply by AIML, or it is improved immensely by AIML. That is true. That is known to all of us. But when we talk about the physical channel and the breaching of the data from the physical channel, specifically in case of satellite wireless communications, where we are talking about wireless communications in the satellite domain, which is predominantly LOS, and the path of communication is very risky and can be easily trapped up by any eavesdropper, that is Eve. Okay, so that part is basically what is happening whenever that communication we think of, the satellite wireless communication, the physical layer cybersecurity, which was almost a static area over the last decade, that is the 5G communications, it has suddenly started getting very high attention, that is on the cybersecurity aspect. So now this secret message here is passed to the encoder in the ELIS. All of us know that a dedicated, just for your information, all of us know that ELIS is a legitimate transmitter and Bob is a legitimate receiver. And what is Eve? Eve is an eavesdropper who is not a legitimate user of the system. So at the ELIS, we are having a secret message which is getting encoded, and that through the open channel, it is going to the decoder of Bob. Now, Bob can receive it, but at the same time, the wiretap channel, through this wiretap channel, which Eve has set up, it can also get the decoding information, because the wireless space or the space communication or wireless communication or satellite communication is very deep in nature, or it cannot control, or it cannot be hidden from anyone. So it will have a channel. But this encoder and the decoder are now tuned with the AIML based modeling coming into the picture. The encoder and the decoder are tuned where the ELIS has its own AIML detector, and the Bob also has its own AIML detector. And when I say detector here, it means both the transmitter as well as the receiver. For Bob also, it is both the transmitter and the receiver. So whatever information Bob is sending to ELIS, only if this entire complex neural network or the DNN is available in the decoder of Eve, only then it can wiretap the channel. Otherwise, no. And only if it has the Bob's neural network or the DNN network, the Eve can decode the signal. And it is almost impossible for Eve to have the constant updation of these DNN structures that are there in Alice's encoder and Bob's decoder. So with that, we are able to wiretap the channel, which we were not able to do previously, because predominantly our entire communication process until the 5G communications, until AI/ML came in, it was mostly statistical. And Eve would always have an idea about the statistical receiver characteristics, but not necessarily that Eve will have an idea about the complete updation of the weights of this AI/ML based DNN structure. And this is where the Eve's decoder will fail, and as such the physical layer cybersecurity will be increased, basically. And this is how it is redefining the cybersecurity at the physical layer level. Basically, a very promising area to work upon, and a lot of funding agencies are funding for research works in this particular domain at present. There has been a debate which I would like to just clear out in a very concise manner about the statistical and the wireless tech on AI/ML fronts. That is wireless technology, which was statistical earlier, and now it is becoming AI/ML. Conventional researchers or conventional scientists are of the opinion that statistical aspects will always stay significant in wireless communications, whereas a modern category of researchers, they say that AI/ML, if we are introducing, then the statistic requirements of having a very deep statistical knowledge of wireless communications or the associated signal processing or random processes will not be any more necessary. But actually, neither of the statements are completely true, or neither of the statements are completely false, because wireless challenges are AI strengths, and wireless strengths are also the ML strengths. So wireless, what are the challenges? Statistics cannot do very hard to model problems, because at hard to model problems, you need to use very high level polynomial orders, which are not feasible in design. But AI's strength is that whenever it is a hard to model problem or a complex problem, it can give you very good representations. Computationally, those hard to model problems become infeasible. AI/ML can give you the computationally realizable solutions, which you can actually program and compute. Parameter optimization is very difficult with wireless, only with the statistical knowledge, but it can modeling of any such complex functions or nonlinear functions is easy job when it comes to AI. And dealing with nonlinearity is also tough for wireless. AI can easily do the nonlinear functions. So you can see the problems with statistical characteristics are compensated. The problems with statistical characteristics are actually compensated by the AI strength. So AI is supporting or aiding the wireless conventional wireless system or the statistical wireless system, and it is not taking away the essence of the statistical aspects. The essence of real statistical aspect will always be there in the wireless communications. I, as a physical layer wireless communication researcher, completely believe that. We can have, for next gen wireless, statistical models can be integrated with AI/ML, just as I have told you in the previous slide. This is a live example of it that was published in the wireless personnel communication and also in the Tech Open, basically. So here you can see this is a structure, a DNN structure through which you are training the data. And after training the data, you are fitting in the resultant parameter. You are basically fitting in the resultant parameter as a fitting model parameter to one of the statistical units. What is this structure basically? You can see on the right hand side. This is basically the Markov chain. So which is a purely statistical structure, and this state transition diagram essentially represents this type of a matrix, which any researcher who is familiar with wireless communication would understand that this is nothing but the MIMO channel, actually M cross N or a NR cross NT MIMO channel. So that MIMO channel parameters we are trying to fit in based on the DNN structures. So essentially, this part is statistical and this part is AI/ML based. So AI/ML based structure is aiding the statistical characteristics, or it is helping the decision making of the statistical characteristics, based on which we are calculating the error, and we are also giving us the feedback, and the process is continuing in a smooth manner. So this is how we aid Markov, or we aid the statistical characteristics using AI/ML based models, basically. briefly to run through one of our works that we have carried out, where we have integrated AI/ML based approaches with statistical characteristics. We were designing basically a short-range wireless communication setup in the millimeter wave regime, where we would have transmitters and there would be LOS as well as non-line of sight paths. And we are observing it not only in a closed geographical area for short-range receivers, but we were also observing it for the long-range receivers. And this was basically the structure where the entire communication was done with all the conventional communication models, or all the conventional communication designs that were established. And this particular structure, if you see, that is the millimeter wave MIMO correlated channel modeling. If you observe this particular channel modeling, because this work is completely on channel modeling, firstly, we are modeling the channel as a baseband channel. Then we are trying to incorporate the essence, or incorporate the effects due to the correlation. For that, we are using the Kronecker correlated millimeter wave channel. And after that, we are doing the equi-correlated millimeter wave channel modeling to reduce that correlation and to increase the performance of the system. So here, this work was published in the IEEE Access. Basically, in the IEEE Access, it was published as a full-fledged IEEE journal. So this was one of the work where we could integrate stochastic and AI/ML designs. This is another work where we could see, this was a work by Silva again in the Journal of Wireless Communication Network, where he could design an entire OFDM-based wireless communication system. Just that for the principal component analysis, that is for the symbol mapping part of the thing, all of us know that principal component analysis is basically a completely statistical process. But here, instead of using the principal component analysis in its basic form or in its own form, this particular PCA, it was designed as a DNN network with a number of layers, where you could see around 4 layers of structuring were there, where the first layer was wavelet decomposition, second was a thresholding, third one was for the reconstruction of the wavelet, and fourth one was to evaluate the principal component. So this was a PCA analysis completely based on the DNN. So if you observe the structure in totality for channel estimation, it is completely statistical. The PCA has been redesigned using an AI/ML based approach or a DNN based approach. And that this is how it is. AI/ML is aiding the conventional wireless communication. We are almost approaching the end of the lecture. AI/ML aided stochastic beyond 5G performance parameters. This was the paper that we could publish in the IEEE journal of late. And if you observe the channel modeling that I had done, comprises of the Robert Heath's reference number 5, where we are using a AOD AOA based dictionary of this type, where equation 1 represents the dictionary basically of all the possible AOAs and the AODs. And from there, we could have the channel matrix, which comprises of these terms A, B, C, and D. And the A, B, C, and D of the conventional MIMO, it got replaced and it got incorporated through the transmitter and the receiver steering vectors, or the angle of arrivals and the angle of departure. So we could observe that the channel states or the channel matrices itself, or the matrices values, are dependent upon the steering vectors or the response vectors, or you can say the AODs and the AOAs. So based on that, we could do the performance analysis of the average symbol error rate and could deduce the closed form expressions through AI/ML based modeling. And we could observe that this particular error rate was ultimately dependent upon big omega and big sigma, which are basically the correlation matrices. Same with the average SER, and the same could be reflected for uplink SER also and the downlink SER also, as well as for the asymptotic high SNR SER in this regard. So now here we could observe that if we consider the statistical states, that is rho T and rho R, which are entities or entries into the correlation matrices at transmitter and correlation matrices at the receiver, then we could observe that they were dependent upon the matrices A, B, C, and D. So this correlation coefficient, which would be the entries of the correlation matrices, are dependent upon the statistical states or the states of the angles. So by tuning the angles, we could reduce or increase the correlation, and thereby we could affect the performance, because the performance is dependent upon the correlation matrix. Performance here means the error rate. It could be reflected to any other performance as well. So now this is the theta T model where for the practical angular variance based model, we are considering that we are varying the actual angle theta T by a margin theta T cap and the actual angle theta R by a margin theta R cap, and that way the transmitter and receiver correlation metrics are represented by these two equations 26 and 27. Based on this, when we if I move into the results, based on this, if we would perform the different simulations, we could observe that the consistently for different results, the low correlation case would yield lesser SCR as compared to the high correlation, medium and the high correlation cases. Similar was verified for different structures, that is different antenna configurations. We could observe it for as high as 256 configuration. It was found consistent over the different modulation schemes starting from BPSK and the different versions QPSK, 4PAM, BFSK minimum correlation as could be observed by us. Similarly, with the low correlation states, if you could observe this figure on the right, it gives a very interesting observation. I am observing the SNR in dB for very low margin here from minus 20 dB to minus 10 dB, where the SNR or the signal power is very, very scarce, which is happening in the remote applications like space communications or underwater communications. And even at such low levels of SNR or low levels of SCR, we are able to get with this system very, very low performance or very, very low SNR values or very, very low symbol error rates basically as compared to the SCR SNR level. And the same was also observed for uplink. The earlier one was for downlink and this one was for the uplink case. So we could get it. If we compared our system with the conventional completely AIML based systems, our system was a semi AIML, semi stochastic model. So if we could compare our design with the different other designs, our system gave a drastically better performance, as you can observe. Yeah. So this is the thing. So we are almost towards the end. So now this is a work where we have incorporated or combined AIML with the stochastic approach in wireless communications, which I would like to leave upon with you. And that in the similar manner, any such stochastic work that is available in the wireless communication that could be modernized or that could be reincarnated through the AIML or DNN based approach. So before we stop, I have a video for you, one last video where we would see what we could expect in the future coming days. Let us be the change that we want to see in the world in 2030 with the advent of 6G network. So for that, with that in mind, let us watch this video. I hope all of you will like the video.
Imagine a world where your device is not just connected, but intelligently anticipates your needs. Welcome to the future with 6G and AI. As we stand on the brink of a technological revolution, 6G promises to transform how we interact with the world around us. But how do we harness its full potential? Thanks to artificial intelligence.
Can you kindly give me a feedback whether the video is moving at your end?
Intelligently anticipates your needs. Welcome to the future with 6G and AI. As we stand on the brink of a technological revolution, 6G promises to transform how we interact with the world around us. But how do we harness its full?
Okay, I understand that the screen is stuck. Yeah, okay. I'll just try to do it. Just give me a moment. Just give me a second. Just reshare the screen.
Imagine a world where your device is not just connected, but intelligently anticipates.
Just give me a second. Okay, I'll just show it to you offline. Yeah, there was a problem. I will just reshare the screen. Yeah. Yeah, I'll just play the video directly. You can just give me a feedback whether you are able to see or not.
Imagine a world where your device is not just connected, but intelligently anticipates your needs.
This is fine now. You are able to see the screen moving.
It's okay now, doctor.
Okay, okay, okay. Yeah, I'll just restart it.
Imagine a world where your device is not just connected, but intelligently anticipates your needs. Welcome to the future with 6G and AI. As we stand on the brink of a technological revolution, 6G promises to transform how we interact with the world around us. But how do we harness its full potential? Thanks to artificial intelligence. With 6G, we encounter challenges like unprecedented data volumes and the need for ultra-reliable connectivity. AI steps in as the game changer, offering solutions that redefine communication. Imagine AI-driven networks that optimize themselves in real time, ensuring seamless connectivity even in densely populated areas. Or picture AI algorithms that enhance data transmission efficiency, making delays a thing of the past. Let's delve into practical applications. In smart cities, AI and 6G could manage traffic flows autonomously, reducing congestion and improving safety. For healthcare, think of AI-powered remote surgeries with real-time feedback, breaking geographical barriers like never before. AI also plays a pivotal role in environmental monitoring. By analyzing vast data sets collected through 6G networks, AI can provide insights into climate change patterns, aiding global conservation efforts. As we explore these possibilities, it's clear that AI isn't just an add-on for 6G. It's an essential pillar that supports its structure. Together, they form a synergistic duo, driving innovation and unlocking new horizons. In conclusion, the integration of AI and 6G isn't just about faster speeds or better connectivity. It's about creating a smarter, more responsive world. As we prepare for this next leap in wireless technology, the possibilities are truly endless, and the future is within our reach. Stay tuned as AI and 6G reshape the world as we know it. Connect with me for more insights on AI in 6G. Imagine a world where your device is not just connected, but intelligently anticipates your needs. Welcome to the future with 6G and AI.
Okay, so with this video, we could understand that definitely as we pave the path towards 2030, and as the entire world is working or dedicatedly working towards the advent of 6G. So as Asian countries, as a larger, not only with India, but as an Asian country, all of the Asian countries as a consortium with India, Sri Lanka, and all our other brothers and sisters, we should work together jointly towards different research dimensions so that we could have the world that we are actually thinking for us with the advent of 6G networks, and we could overcome or eradicate the limitations of the present 5G networks. So with this thought, I will leave you behind. This is our collaborative group. We have our different students from the diploma level as well as from the graduation level. We have different collaborators from we have also the research scholars in our university. We have different Indian collaborations. We have collaborations with the University of South Florida. We have other collaborators from UG and PG levels. We have collaborators from different Indian universities. Chandigarh Engineering College, very popular university. Then many other collaborations with reputed institutions, Assam Engineering College, NIT Silchar. We also have collaborations with San Diego State University, UEL London. We have collaborations, and slowly I'm starting off exploring my horizon towards Sri Lanka. I would love to have different collaborations with the different universities. We have started with Dr. Pasan Maduranga. We have collaboration with University of Sri Jayawardhanapura, Sri Lanka. Thank you so much. Thank you for having me over here. Thank you for the kind invitation. I would like to thank Engineer Chamila Prabhat, the Honorary Secretary of IET Young Professionals Network, Sri Lanka. My special thanks for Ravidu Herat for all his coordination for organizing this webinar. My sincere thanks also goes to all the organizers and coordinators at the IET Young Professionals Network, Sri Lanka. I hope the session was okay and the session was beneficial for you. and the participants could gain at least some insights. Obviously, the entire domain cannot be covered in just 1 hour, 1.5 hours, but I hope the participants could draw some insights at least from the deliberations. With this, I leave you all with my lecture, and I would love to interact with you and take up some of your questions. Thank you so much. Thank you. Over to you, Ravidu. Thank you. Yeah. So if anyone has any questions, I would love to answer it. Else, it is over to the organizers, please.
Professor, thank you so much for the insightful session. I actually personally learned a lot, and I'm really interested in jumping into the research arena of digital signals processing. So I had a few questions to ask you, and
Yeah, sure.
So I'd like to begin off by
This is
asking.
Linux, right? This is Linux,
Yeah,
right?
Linux.
Okay, okay, Linux. Okay, okay.
So
yeah, please go ahead.
Thank you. I wanted to know if there were any specific research gaps or challenges in the integration of machine learning 6G with 6G technologies, especially around the physical layer or the signal processing layer, that any early career researcher could focus on.
Yeah, so to give you a very nice question, actually, to give you an insight, there are number of research gaps actually. Okay, so if I touch upon some of those, I have already I have already mentioned some of the aspects. If you could follow in physical layer, I touched upon two very important aspects. One is basically related to the channel estimation aspect. So the channel estimation process, if you consider the channel estimation process, the conventional one without the AI/ML integration, the channel estimation process is a highly stochastic process, a very sturdy process in terms of having very deep knowledge on the statistical models, in terms of having very core knowledge about random processes, statistical signal processing. You need to have a very, very in-depth knowledge. Whereas with the AI/ML coming into the picture, minded, there is a complete paradigm shift where you are actually trying to remove the complicated mathematics out of the picture and you are going towards a data-driven approach. So the moment now you go towards a data-driven approach, it is okay when we are talking about categorical data, IT applications, higher end communications like the application layer, the application layer or the session layer, where we are having limited data sets to train the system. But when it comes to physical layer minded, we are playing with, or we are dealing with basically amplitude levels, or we are dealing basically with the signal magnitude levels or the phase value levels. Now, those phase value levels, how much of the phase values would actually be, or how much of the amplitude level training would be actually required if your model has to accurately estimate the channel, that estimating that how much of the signals or how much of the pilot signals will be necessary and how much of the pilot signals could you let go. If you are training your models with an AI/ML based approach, then that optimization of the system is itself a research gap. The optimization of the system, that is, how much of it would you treat it like the previous generation pilot signal based approach, and how much of data will you actually train your system with to optimize that and to still get a good result out of your channel estimation process. That is a very deep research gap, and that is a very core research gap, and on that a number of researchers are working upon. If you are interested, I can also, if we get connected over some medium like emails or maybe through LinkedIn or something, we can definitely, like, I can share with you a number of papers where researchers are working on, even I am working on with some of my research students on the optimization of the pilot signals. How much of the pilot signals are necessary, because pilot signals affect the spectral efficiency. So we are trying to get a ideally we are trying to get a zero pilot system, but that is not possible in practice. So how much of the pilot signal you will be able to reduce so that your spectral efficiency is also good, but at the same time the training is also good so that you can estimate the channel. So that is a big research gap that is in the direction of channel estimation. If I would throw light to you at physical, or since you mentioned mostly about physical layer communication, another very key aspect is related to the radio resource management. We know that in the 5G domain, we were having aspects like NOMA, the non-orthogonal multiple access. We were using different such radio resource allocation mechanisms. But now we are talking about sub-carrier management. So where that we have to optimally allocate not only the carriers, but we have to optimally also allocate the sub-carriers. So that allocation of the sub-carrier will need AI/ML architectures, but at the same time, AI/ML based software algorithms, remember, but at the same time, it will also need the equivalent architecture, which will take care that you are actually able to physically assign the accurate sub-carrier to a particular user that you are trying to deploy. And in that, you cannot use the simple AI/ML based approaches. You have to use the AI/ML based algorithms with the quantum aspect associated with it. That is basically you have to use the quantum AI or the quantum ML. In today's lecture, unfortunately, due to paucity of time, I could focus only upon the AI/ML based approach. There could be a different session altogether if we talk about quantum AI and quantum ML based approaches. So that is another research aspect, number 2. And number 3 is, I have already shown you modulation detection. With receivers now being essentially software programs, your system could receive any signal with any type of modulation format incorporated in. So the receiver that you are developing has to be a AI/ML based receiver, which will flexibly change from one type of receiver, say the QAM receiver, to the PSK receiver. Again, in QAM, it may change from a 4 QAM receiver to a 16 QAM, 16 QAM to a 32 QAM, 32 QAM to a 64 QAM. Now, how that will adaptively change and what kind of logic or what kind of modeling you will do so that there is a synchronization between the modulation detector, means the modulation recognition, and the modulation detection, that is the actual reception of the signal. So that synchronization is a gap, like how you will synchronize that or how you will detect the different types of modulation schemes. So 3 things I have pointed out. One is related to the modulation. The other is related to your spectrum resource allocation in the sub-carrier level. And the third one I have allocated, basically, it's your basically about the channel estimation. So in these directions, if you are an interested researcher, these are the directions that you need to follow. And any mode of collaborations, any sort of connect you need, any help you need, please feel free to reach out. Yeah, so I hope I answered your question, Lino.
Yes,
Yeah.
Professor, thank you. But I have a little bit of a follow-up question, especially
Yeah, sure.
regarding the channel estimation part. So you
Yeah.
actually mentioned there the use of quantum computing for further analysis of signals. So how could like somebody in like a university student, because we have limited resources and we don't really have access to quantum computers. So how can we sort of approach such a project with limited hardware access?
Okay. So the firstly for when it comes to channel estimation aspects using the quantum computing dimensions, the major aspect of quantum computing that will be used there is the QKDs. QKD basically means you can note it down. It's the quantum key distribution. Please have a look over Google, quantum key distribution. So that is basically the key essence of your quantum computing that is basically used in the wireless channel estimation of the quantum based wireless communication. So basically QKDs are some unique keys that will adaptively change at the transmitter and adaptively change at the receiver, so that your channel in between becomes sort of a decoded channel only between your intended transmitter and the intended receiver. So now if you are having the synchronization of the QKD, that development of the QKD, if you can do properly, then that communication chain, you can have a good communication link or a reliable communication link only using the QKD. Coming back to the second part of your question, where you asked that how as a university student you can have access to such quantum computational aspects. Mind it, development of the QKD or design of the QKD is a very simple. You can go through the internet. I can also provide you materials or papers where you can see how QKD algorithms are developed. QKD designing is not very difficult. To design quantum computing based full-fledged algorithms is I should say it is rather terse, or you need the necessary hardware arrangements with you. But for only for the QKD designing with your MATLAB or with any of the programming languages like Python and all, you can design the QKD only with the use of conventional computers without having the proper resources at hand as well, because QKD structure is such that it can be a normal binary decisioning computer version of the QKD can also be designed, and you can test that over the quantum hardware. And when I say quantum hardware, I am not meaning very costly hardware. You can buy a few number of qubits, quantum bits, as the QSKIT software or the QSKIT bits that are available under IBM. I am sure any of the universities will be at least able to help you procuring at least 4 to 5 number of QSKIT bits. Actually, even we are facing that hurdle with quantum research that if we need many QSKIT bits, say 64 bit, 128 bit, it's difficult, but at least 4 to 5 QSKIT bits can be provided to you. And with that, in wireless communication, it is sufficient to do the QKD based channel estimation work. That much I can assure you. Lina, is your doubt clear in that regard?
Yes, Professor. Thank you. It actually cleared very well. Thank you so much.
Yeah. Thank you. Thank you. Any other questions on the chat box, I guess? Yeah. Okay. There is a question, I guess. Yeah, there is something from there's something, if I'm sorry if I'm not pronouncing the name correctly, Nanayakara, I guess. Dear sir, are there any applications of NLP that help explain wireless classification models or give insights into physical layer threats? This is the first question. There is another question, I guess. Nanayakara, if you are hearing me, if you are there, am I audible to you? Am I audible to you? Could I unmute? Yeah. Okay. So if you are asking about NLP, that is natural language processing, actually there might be some applications in the domain as well, but as far as physical layer security threats are concerned, in the threat based domain, actually NLP based approaches will not really be a very ideal approach for that type of aspect. Actually, the reason being, because when I was talking about physical layer security, I was mostly talking about physical layer security in context with the satellite or space network. So if I'm talking about that satellite or space network aspects, actually what happens is at that time you will not be using very heavy or very highly overloaded or overhead based systems like the NLP based architecture. So for the classification purpose, yes, for suppose if it could have the NLP based approaches, or for the classification models in modulation recognition, suppose out of different types of modulation you are trying to classify only 2 or 3 types of modulation, they are actually that NLP based approach that you have mentioned may come into the picture. But for physical layer cybersecurity, I am not sure. There may be, but mostly as far as the concept of NLP comes in to me, it would be very highly, it will be a system with very high overheads, and that would not be very highly well appreciated when it comes to satellite based or space based networks due to the power constraints. Actually, that is your first question. The second question was, can we use feature engineering based conversational machine learning to classify in signals in physical wireless based physical security layer? Yes, that is very true. Very nice question. Yes, we can use the conversational machine learning based approach. We can use the generative AI based approach where we are prompting the systems constantly. There is a paper, if you wish, if you share, if you'd like to know, maybe I can share it with Ravidu. There is a recent paper by Cornell University on the generative AI based designing of MIMO wireless systems, where they are talking about the conversational machine learning based approaches to the design of wireless communication, and also for the classification purpose in terms of modulation or channel estimation or that type of aspect. There, Gen AI and the conversational based aspect can be very widely used. So that way, this second part, yes, it is a very relevant question. It can be used. Research has already started, very new research, and if you are interested, you can jump into that research right away. Actually, this I am talking about a paper of March 2025. The paper that I am talking about, Cornell University published it in one of the transactions. Yeah. So I hope I answered your question, Nana. Sorry to pronounce your name, Tatsara. I hope I answered your queries to your expectation. Yeah, please.
Yeah, thank you, sir. It's interesting.
Yeah, thank you. all of you, please also try to explore the recent researches that are going on through the internet. Actually, I will share some links with Mr. Ravindu as well for this for your search. Maybe he can share it with you. Yeah. Any other questions? Any further questions? I would love to answer.
Excuse me, Professor, it's me again. I actually have
Yeah. Sure.
another
Please.
follow-up question. So you
Ah.
mentioned about using pilot signals beforehand, right? So can't we like do some research based on pilot signals where we use a very cost-effective medium for the transfer of these pilot signals and then transfer it over to a more expensive 6G bandwidth?
Yeah, that is obviously because the thing is actually this model that I am talking about is all minded at the baseband, the QKD based approach, the pilot signal estimation or the pilot signal incorporation and the estimation of the pilot signal. It is all at the baseband level here. It will be done mostly at the baseband layer level signal processing. That is, we all of us I think if you would have gone through your basics of wireless communication at the base level for any physical layer level signal processing, whenever we use the term signal processing, we are having the baseband equivalent model where the up conversion of the frequency to the desired band is actually happening only at the end, that is transmitter end, and at the receiver's beginning again that frequency is getting cut down, and the rest of entire processing is done at a very cheap or accommodatable medium, that is at the baseband level, at nearly zero frequency level, with the baseband symbols getting processed, and the pilot incorporation is also done at that level only. But the question is that where that pilot itself without the frequency, or when the frequency is incorporated, the amount of the pilot that you are using, how much ever pilot you are using, that would lead to the spectral efficiency loss. Actually, more the pilot it will be there. So the essentially it's now essentially we are trying to develop a zero pilot system, or a system where there would not be any requirement of this pilot signal, because it eats up the unnecessary bandwidth. But now the problem is that the training models also have a limitation because of the computational power. So you have to optimize between how the more you give pilot signals, the lesser training is okay for the system. But the more you train, the lesser the pilot signal requirement becomes. But you cannot make either of them zero because both are constrained. Modeling cannot, the channel AI models will be limited because of computational constraints. Pilot signal also you cannot make it completely zero because you have a limitation with the processing. So you have to strike a balance between both of the two, that say for with 20% of the pilot, instead if earlier the conventional systems were using 30 or 40% of the pilot, now you are with the incorporation of the QKD, you are able to reduce the pilot signal to 20%, or you are able to reduce the pilot signal to 15%. So it's a combination where introducing that QKD using AIML based algorithms, you are able to reduce that pilot signals, and the lesser the pilots, the more the bandwidth efficient your system is. Am I clear? Am I clear in that part, Lino?
Yeah, that part I think it's clear now. But
Yeah.
so will a similar structure be followed even for the aided beamforming and aided beam management?
Yeah, actually, beam forming and beam management are quite contrasting in terms of are quite contrasting as applications in terms of, although the similar approaches are there, but they are quite contrasting in terms of the applications. Like for channel estimation is a totally different application, and beamforming is a totally different application. However, yes, at the base level, yes, the same approach. Even if we are doing beamforming, don't have that incarnation. When I am talking about the beam, I am essentially only talking about the vectors or the baseband vectors. There will be a matrix or a one-dimensional row vector or a column vector, basically, which will trigger the entire baseband processing. And that baseband processing, if we are doing that necessary equation implementation, if we are doing, we are ensuring that the signal is already beamformed. It is not that for having that beam, we need the actual antenna structure of the beam and we need to have the frequency shooted. Yes, for the RF level communication, that will be necessary. But for the signal processing level, yes, the same baseband modeling will be there at the back end. And just in that baseband or low frequency, zero frequency model, if you are incorporating some quantum based approach, like you are integrating the beamforming with some quantum key, or you are integrating it with some AIML based algorithm, that much is sufficient for that. It does not need a high frequency translation. You don't need to process anything at the high frequency, actually, because if you do that, actually the sampling rate requirements will be very high. So we generally avoid processing anything at that high frequency. That is, I think, a concept of like a baseband equivalent model. If you go through the baseband equivalent model a bit more clearly, that concept will be clear. Entire processing, everything that I have spoken to you in wireless communication, it is all, I have not spoken anything at the RF level. I have spoken only at the baseband level. I hope it is clear.
Yeah, that actually cleared a lot of doubts. So again, when we are using a lot of these quantum computational aspects,
Yeah.
so should there be quantum computing resources locally when these systems are connecting, or can they just work on binary systems?
They can work. They're already, because of this resource, the resource constraint is not being faced only at your end. Even very advanced countries, like I am collaborated with US universities, they are also facing that similar type of constraints in terms of buying or working with procuring or working with very high level of very high number of qskit hardwares, actually, or qubits, basically. So all of them, like many researchers towards the initial stage of quantum computing, have already developed ways and means where these quantum structures, like the QKDs I mentioned about, or such similar other structures, already there are binary representations or methods of developing the QKDs on the binary computers. That type of systems have already been developed. So you can test, maybe not fully at the quantum hardware level, but with your binary hardware level, you can easily test your structures. Actually, you can easily test your different types of algorithms. So on your binary computers itself. However, yes, for testing it on a real scale, a fully real scale, you will need the quantum resources. But for an early career researcher, as you mentioned, it is more than more than good to start off with the binary computers. Is it clear? Yeah.
Yes, thank you, Professor. That actually cleared everything. It was really helpful. Thank you once again.
Yeah, no problem. No problem. Well, best wishes. Yeah. Yeah, I think if there are no further questions, over to you, Ravidu sir, please. In greater interest of the students, I'm just sending my email ID I'm sharing my email ID over this group or over this meeting link on the chat box, so that if anyone is interested towards any sort of collaboration or any sort of research work with me, you can directly contact me. I am also available on LinkedIn. I am also available on ResearchGate. So you can contact me there as well. I have shared my email ID.
Okay, thank you, Dr. Sabyaji. So, on behalf of IIT Yamprabha and Sri Lanka Network, I want to thank Dr. Sabyaji Bhattacharya. So, for your it was a really insightful session. I hope all of the participants understand how AI helps to understand the uh, wireless communication. And so, I want to thank all the participants as well. So, I think we can end the session now. So, thank you again. And have a good night.
Can
Thank you very much.